This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So we'll continue our discussion on frequency domain compensation. Yesterday we saw how to translate performance specifications into the shapes of body diagrams. And today we will introduce the first compensators, like the basic compensators that you can use when designing controllers in frequency domain. You can combine, we will present some basic compensators, but you can combine them. So I will explain that as we go. All right, so I will first briefly overview the performance specifications that we covered yesterday, and then I will go through a list of various compensators. They're called lead or PD, lag, PI, lead lag or PID compensators. And I mean, we covered this yesterday, so fundamental limits. So I won't talk about that today. And just conclusions. So what we saw yesterday is that, you know, open loop body plots can capture a range of different performance specifications. Since the open loop transfer function is a product of the plant and compensator or controller transfer functions, given a plant transfer function, we can search for a controller transfer function that achieves certain shapes. So in other words, satisfy certain specifications, right? So the idea is to shape the open loop transfer function to achieve, or its body plots, to achieve required design objectives. So because we have a sum of the plant and controller transfer function or body diagrams, you know, we need to learn some basic controllers and their body diagrams so that we understand what sort of body plots we can add to the plant body plots, all right? So today's lecture is all about that. So then we will be able to pick, so part of the design is to basically to pick the right controller transfer function in order to compensate plant dynamics. In other words, we are shaping the body loop by the choice of compensators. All right, so what we saw yesterday was that lots of different performance specifications can be captured by the shape of body diagrams. So if we look at the magnitude at low frequencies, so typically we would want magnitude of the open loop transfer function to be above a certain value, which would guarantee certain tracking, right? We saw that around crossover frequency, we would like to achieve a certain phase margin, which is related to overshoot, right, and stability, right? And then also the crossover frequency is related to rise time, how fast the system would respond. And then we also saw that, you know, at high frequencies, we want typically to have a gain to be lower than a certain value in order to attenuate measurement disturbance, measurement noise, right? So, all right, so now what would be the design question? Well, if I give you plant, right, dynamics, and I give you specifications, so you would plot first the plant body plots, and you would see how they compare with the given specifications. So typically, the specifications would be not met just by plant transfer function, right? And then typically you would need to design a controller so that when you add controller's body plot to the plant body plot, you do satisfy performance specifications. So that's roughly what you would do every time you are asked to do frequency domain compensation. This technique is called loop shaping because we are shaping the open loop of the closed loop system to achieve various objectives, right? All right, so that's all good, but now we need to go through a catalog of different possible controllers that we can use, and we need to learn their body diagrams very well. This is like Lego, right? So I'm teaching you each of different compensators is a different Lego block. So you need to build something, and you need to know how to use these Lego blocks to basically satisfy some constraints, right? So so we will now go through certain basic elements or blocks or compensators that we can use for compensation by body. All right. So these are the basic elements. Lead control, proportional derivative control is a special case. Lag control, PI's proportional integral control is a special case. And lead lag and PID is a special case. We will first introduce each of these, and then we'll consider some examples. The examples I will present are just qualitative. I won't be calculating the pole zeros of the compensators and gains. We will do that in the following lectures. But today we will just discuss qualitatively, what sort of effect, different compensators might have when, they are used for compensation. All right. So, by the way, you need to learn these compensators very well, and you need to, in particular, learn the degrees of freedom. There will be some parameters that you can tune, right? So each compensator will have several parameters that you can tune. We saw a similar situation in PID controllers. You had proportional, integral, and derivative action that you could tune, right? And tuning of these PID controllers was not easy. We saw, okay, Ziegler-Nichols give you some initial tuning rules, but, we did not have a systematic way to choose these parameters. Now, what we will present now will give you a systematic way of tuning PID controllers. One of the compensators that we will consider is lead lag, and then PID control is a special case. So you can do PID controller tuning using body diagrams, using the techniques that we will present here. All right. So that's a very systematic approach to tuning PID control. So here is the first compensator. It's called a lag compensator. By the way, lead and lag compensators would look very identical, except that the devil is in the detail. So they will have the same transfer function that would look pretty much like this, but then there will be difference here. So here we are assuming for lag compensator, we have that tau z is smaller than tau p, and both of them are positive. What would that mean for pole and zero? So what is a zero of this system? What is a zero of this system? -1 over tau z, right? And what is the pole? -1 over tau p, right? So which one is closer to the imaginary axis? Because tau p is larger, that will be closer, right? You're dividing one by something larger, right? So that's why I'm saying that this guy has real pole and real zero. They're both stable, and pole is closer to the origin than the zero. Note also that we can play with this constant k. So note that the DC gain, so C at 0 is just k, right? And then C at infinity is k over tau z, tau p. You can simply get that by just letting S going to 0 or to infinity. Why are these important? So what do you think this magnitude body plot would look like? What would this look like? It consists of three parts. It's a product of the constant k, then this part, and then 1 divided by that, right? So you need to remember now what is a body plot for each of these guys, and you need to add them up, right? So does anyone remember what would the... So
it's either a buck that goes up or a buck that goes down.
All right, yes, bump for what? For the phase? Or for the gain? Okay, all right, let's see what it looks like. So for k equal 1, note that what you are adding, so this line here is the first asymptote. This is the asymptote for the pole. Because the pole is closer to the origin, the break frequency would be for the pole first. And then this is the corner frequency for the 0, right? So these corner frequencies are 1 over tau p and 1 over tau z. So this, you need to remember now individual body plots for the stable 0, stable pole, and a constant, and you add them up. What will happen if k is not equal to 1? Or down. So when k is larger than 1, it's shifted up. So what is shifted up? Magnitude plot, but phase stays the same. If we are multiplying with positive constant, phase doesn't change. So we will be just shifting this guy up and down, and phase stays the same, right? So what is very important here is the following. Know that we have this phase lag. Know that phase starts from 0, then goes to some minimum value. There's this negative bump, negative phase. That's why we are saying it's a lag. There's negative phase that this compensator is adding to the loop. And then as omega goes to infinity, again, the phase goes to 0. But it's always negative. The phase that this compensator provides is always negative. All right. Where is the minimum phase or maximum amount of lag? It happens at this frequency, which is 1 divided by square root of tau z times tau p. So look, we presented all the basic body diagrams. Here we added them up and I summarized things for you, because we will need to use this as a single block, right? So this is one of your Lego sort of blocks that you can play with. So what you can play with here is, tau p, tau z, and k. So we already saw how k affects this body diagram. So k positive will shift magnitude plot up, larger than 1, and k smaller than 1 would shift the magnitude plot down without changing the phase. Now what happens if we stretch? What happens if we stretch these corner frequencies? Well, this bump will go, lower, right? So the maximum amount of bump we can expect, we can get close to, maybe 90 degrees, because both pole and 0 would add only plus, or minus 90 degrees of phase, right? So when you add the two, you cannot expect to have more than 90, right? But typically it's much smaller than that, right? So at which place does this happen? Well, at the frequency that is given there, 1 over square root of tau z, tau p. So now, what are your design parameters? Tau z, tau p, and k. So if tau z and tau p are close together, there will be less lag provided, right? If they are more stretched, there is more lag provided, right? And then, obviously, k can shift things up and down, magnitude plot up and down. So, all right. Now, how can this be used in compensating the loop? So here is one picture. Now, this is qualitative. This example is qualitative. It's not supposed to give you exact numbers. We will do a lot of computations for specific examples later on. This just illustrates what's possible. So the brown line brown body diagram. I said it's uncompensated plot. That's actually plants' body diagrams. So plants' body diagrams are brown and they are uncompensated body plots. And when you add this sort of compensator to plant, what you can do? Well, you could basically increase. So what I can do, I can pick k larger than 1, so that this line becomes really 0. So I will have some gain for small frequencies, and for high frequencies, I will not be adding any gain, right? And I will still have this lag, because by shifting this thing up and down, I don't change the phase. So when I add something like that to the plant, dynamic plant uncompensated plot, the compensated plot would lose some phase at the point where, especially where this bump is largest, right, in magnitude, but we can increase the gain at low frequencies without affecting the gain at high frequencies. So that's what this shows. So gain at high frequencies is not affected. We increase the gain at low frequencies, and there is this bump that we need to deal with, right? So if you basically have this situation, what this would help you with? I mean, when you think about performance specifications that we might want to impose on the compensated loop, what does this compensator then help us with? Tracking, steady state errors, you know, so the low, we increase the gain at low frequencies, right? So that would help with tracking, right? Now, note that the undesirable effect here is that this lag might, you know, well, it would reduce typically the phase margin, right? So the phase margin would typically be reduced because you are subtracting the phase that compensator adds. So reducing phase margin, what does that mean? Well, we might lose stability, right? We might lose stability, but even if we are stable, what would happen? Overshoot would be larger, right? So note that all the compensators that we will be using, they might help in one sense, but they may sort of screw up something on the other side. So you have to keep in mind all of these different things so that you don't destabilize the system. You say, okay, I improved my gain at low frequencies, tracking would be better, but you destabilize the system, so there's no tracking, right? So you have to be very careful about that. Now, one question, can you increase phase margin by adding a lag compensator? Can you increase phase margin? No? Sorry? Okay, but okay, if K is positive, what do you mean? If K is positive, then no.
We can't shift it up if K is positive. It's negative maybe.
All right. Okay, so this is one answer. So the answer is no, and there's an explanation. Any other opinions, or everyone agrees? Yep.
Because it attenuates the high frequencies, you can move the crossover frequency to a lower frequency when the phase is better. So yes. Excellent.
That's what I was looking for. Yes. So the answer is actually yes. You can increase phase margin. So what you can do is note that this guy, if you used it exactly this way, you can, by adding this magnitude plot to the plant magnitude plot, what can happen that compensated plots crossover frequency might move this way. If the gain is, let's say 0 for the compensator, so crossover will move to the left. Typically, uncompensated plant would have excess of phase at low frequencies. You remember when we were plotting different body diagrams, typically there is plenty of phase margin, right, in low frequencies. In high frequencies, typically, you have less phase. So by exactly this mechanism of shifting the crossover frequency to the left, where the uncompensated plant dynamics has excess of phase, then by adding, this negative phase from the compensator, but still using much more excess of phase in the plant, you can actually increase the phase margin. So it's a very interesting phenomenon. Now, what is undesirable if we do shift the crossover frequency to the left? What is then undesirable? So we increase the phase margin. Suppose we increase the phase margin, and we then decrease the overshoot, right? So, but crossover frequency then was related to what? Rise time. So rise time would be more sluggish, right? So you will have longer rise times, so the system would be slower. So smaller crossover frequency would mean your system is slower. It will be slower to respond. So while you might increase the phase margin, you also increase the rise time, which is typically undesirable, right? So you can see now how just this one element, you know, has a lot of degrees of freedom, and it can be used in a very versatile manner. Now, the things that you can play with and you can tune are tau p, tau z, and k. And you can achieve all of these things we discussed, right, by carefully designing k, tau z, and tau p. Right. And we will look at different examples where we, you know, achieve different objectives by choosing specific values for tau z, tau p, and k for a given plant. So I give you the plant, I give you specifications, and then we will calculate tau z, tau p, and k. So that's what we will be doing this afternoon. All right. So PI compensator is a special case where, you know, the pole, is now at the origin, right? So note that in the lag compensator, tau p was, you know, large. If tau p is infinity, right, then, you know, we have, that if tau p is sort of, it's obviously not good to write it in this way, but if I divided everything, so I have s plus 1 over tau p, if tau p is infinity, that becomes an integrator, right? So integrator, right, here can be like considered a special case of the like stable pole. Pole arrived at the imaginary axis, right, with our choice of tau p. So actually, PI compensator can be considered as a special case of a lag compensator. Again, well, in this case, you have less degrees of freedom. You only have k and tau z to play with, right? And what is the LEGO in this case? Well, this is what it looks like. Right? This is, again, plotted for k equal 1, right? So note that for all frequencies, this behaves pretty much like an integrator, and then, you know, when you have zeros affect quarter frequency here, 1 over tau z, then it just sort of straightens it out because you add pole and zero body plots together. So this is what you get in the end. So you need to also remember, you know, this sort of compensator because you might need to use it. And the degrees of freedom are k and tau z. Right? By playing with tau z, you can move this quarter frequency, right? And by the way, you will get 45 degrees or minus pi quarter, right, at this frequency 1 over tau z. Because this thing here is like symmetric, right? So, all right, so we are just presenting different Legos, right? You need to be very familiar with these guys because in the end you will need to play with different degrees of freedom to achieve different compensated loop characteristics. In Ogata, in Franklin et Powell, you have a range of different examples. So once you work through several examples, you would get the hang of it. So it's an open book exam, so you don't need to learn these formulas by heart, but you do need to learn how to use these things, right? Lead compensator, as I said, you know, the transfer function of lead compensator, so this is yet another one. So lead compensator has the same transfer function except for one detail that's different. Now tau p is smaller than tau z. So what does this mean? Well, 0 is closer to the origin than pole. Obviously, both pole and 0 are stable, right? Because tau p and tau z are positive, right? Except that in this case, 0 is closer to the origin than the pole. And you again have that DC gain is K, and the C at infinity is this. So this is the body plot for the lead compensator. So again, the degrees of freedom are K, tau Z, and tau P. This is plotted for K equal to 1. Plots for K not equal to 1, like positive K, either you are shifting up or down the plot, right? So that's easy to obtain from these plots. So what you have here now, at this frequency, 1 over square root tau Z tau P, you get the biggest bump. Know that the phase that this compensator provides is always positive. So this is a lead compensator. Now, where would you use this sort of compensator? How can you use it? What do you think? Yeah, if you have an unstable system, or if you simply want to improve the stability phase margin for a stable system. Because if you add this compensator and you pick this frequency exactly to be at the point where your phase margin is measured, the crossover frequency, then this bump will help add some value of phase to your phase margin. So the compensated plot would have a larger phase margin. All right, so that's exactly what is plotted here, or attempted to be plotted here. So we have uncompensated plot, which is brown, and then if you add the lead compensator so that the largest lead from the compensator happens at the crossover of uncompensated plot, you will add some sort of phase in the region around crossover frequency. Now note what happened when I added so the purpose was to add some phase around the crossover frequency for the uncompensated plot, right? But what we have here is an effect. The crossover frequency of the compensated plot was moved to the right. So we will be measuring phase margin somewhere here. So know that plant may have less phase at that frequency, and then the compensator adds some frequency, but the net effect may not be enough for what we intended to do. So typically, we will design the system by saying, look at where crossover frequency for uncompensated system is, then pick this frequency where I have the biggest lead at that frequency, at crossover frequency of uncompensated plot. But because of this guy, magnitude, this will shift the crossover frequency of the compensated plot here, and then I will be measuring the phase margin then somewhere here. So you will always have to check whether you achieved what you set out to achieve, after you design the compensator. So you always need to check that the phase margin you wanted to achieve is achieved. So this is a common story with all compensators. You will have a certain procedure which is sort of systematic, but it may not give, it's always working with some approximations. At the end, you need to check that indeed you achieved what you wanted to achieve, right? And if you didn't, you need to repeat the process. And we will explain how to do that in future lectures, right? Okay, are there any other questions here? Yep.
In the last conversation, you said if we change gain, we will affect the low frequency response, but not the large frequency response. But shift the whole clock.
Yeah, but if I can choose, what I didn't say, well, maybe I wasn't precise. I was talking about, so we are going back to the lag, right? So I said, let's pick K so that this line becomes 0. Right, so that's what I was saying. But you are right, in general, yeah, of course you can affect high frequencies if you choose very high gain. If you choose very high gain, then this line would be above 0, right? So then in that case, you're right. Mm-hmm. So again, here you have 3 degrees of freedom. Tau Z, tau P, and K. But note that now the effect of the compensator is totally different from lag. Here you are providing lead. And you have more gain at high frequencies. No matter what you do, you would be adding more gain at high frequencies, right? Because of the choice of tau z and tau p. All right. So PD is a special case. You can just do this as an exercise. All right. Here is a combination of lead and lag, and it's called lead lag. It's basically a product of these two transfer functions for lead and lag. And you might ask yourself, well, why would I need this? It turns out in some really tricky design problems that using just lead or just using lag cannot do the job. Your performance specifications are so tight and plant dynamics are so obviously plant body plots plus your specifications for the compensated plot would constrain you. And then using just lead or just lag may not do the job. So that's why we also need to use lead lag. So note in this case, you have these inequalities where the first two correspond to the lead and the second two to the lag. And other combinations are possible. I mean, depending on your design question, you might reverse these two. It depends really on the problem you're dealing with. So what does this look like if we plot body plots? In this particular case, this is what you would get. So you can see that with the choice we work with, lag happens at low frequencies, lead happens at high frequencies. You can reverse them, you know, so it depends on your problem. But this is probably more commonly used. Know that in this case you have 5 parameters you can tune. So all of the taus plus k. So it becomes rather non-trivial to tune these when you are given a specific problem. And we will learn some techniques on how to do this systematically. But as I said, every time you follow those steps, you know, of sort of selecting parameters, you will in the end need to check that indeed you achieved what you want to achieve. So PID control, in this case, you know, we can rewrite everything in this way. So lag compensation pole is placed at 0, and lead compensation pole placed at sort of infinity, right? So you can think of this PID control as a special case of lead lag. Now, what I want to emphasize is the loop shaping or body diagrams design is the most systematic way to do PID controller tuning. So what we were talking about, Ziegler-Nichols and root locus and all of these things, they are not as powerful as body diagrams, all right? So and then in this case you have you know, k, tau z1, tau z2 as parameters that you can tune. So how you can see that? Well, when you multiply out everything, you can rewrite everything in this way. So you can see that you have proportional, integral, and derivative action. So and you know the tuning is very similar to the lead lag compensation. All right. Okay, so I'm realizing it's a short lecture, but we will have another one this afternoon, so it's probably okay. So what we saw today is different body diagrams which you need to really learn how to use. So there are different parameters in these transfer functions that you can tune. These parameters would affect phase and gain plots of compensator body diagrams. And these are actually the, like I call them Legos. I give you the plant body plot, I give you the performance specifications. You need to come up with these Legos. You need to design Legos so that when you add them to the plant plots, you satisfy all specifications. So that's what loop shaping is all about, right? Are there any questions? All right, since we have a lecture this afternoon, I'll just stop here and I'll see you later. Thanks.
If we add in the compensator, then we want to find out the new phase margin. We need to look at this point instead of that one.
Frequency to match. Yeah. You can get an amplitude to match, but she's like, 这样想吗？不是。 方程得写